On September 23, 1999, NASA waited for Mars Climate Orbiter to pass behind Mars. Radio contact was supposed to fade at a precise moment, then return when the spacecraft emerged. But the signal vanished 49 seconds early. It never came back. The spacecraft had traveled more than 600 million kilometers. Its final approach was being adjusted to a narrow target above the Martian atmosphere. Yet the investigation would trace the loss to numbers that looked ordinary, moved through the system without units, and meant two different things to two different teams. A $125 million mission had reached Mars carrying a hidden translation error. During the cruise, the spacecraft used reaction wheels to hold its orientation. As those wheels absorbed momentum, small thrusters fired to unload them. Each firing gave the spacecraft a tiny extra push. Those pushes were recorded in a file called Small Forces. Navigation software used the file to estimate where the orbiter really was and where it was going. No single firing was dramatic. That was precisely the danger. The error arrived as a sequence of plausible corrections, each too small to look like a catastrophe. Over months, the navigation model kept absorbing those pushes. The spacecraft was drifting away from the path the software believed it was following. The contractor's ground software reported thruster impulse in pound-force seconds. The navigation software expected Newton seconds. 1 pound-force second is about 4.45 Newton seconds. So when the file delivered a number, the receiving system interpreted a force more than 4 times smaller than the force that had actually occurred. The values were not obviously corrupt. They stayed within a believable range. The file had numbers, but no enforced unit contract strong enough to stop the transfer. No type system rejected the mismatch. No end-to-end test exposed it before flight. This was not a calculator giving the wrong answer. It was two correct programs agreeing on the shape of the data while disagreeing about its meaning. As the orbiter approached Mars, the predicted trajectory and independent observations did not line up cleanly. Navigators saw unexplained differences. Concerns were discussed. The team kept updating the model and working the problem, but the discrepancy never became the kind of stop signal that forced the entire chain to be challenged. There was also a possible final correction, called TCM5, that could have raised the closest approach. But the contingency was not ready to execute. The analysis, procedures, and testing needed for a late decision were incomplete. The warning existed as fragments, unexpected navigation residuals, informal concern, a correction option without operational readiness. The organization never assembled those fragments into one clear message: do not continue on this trajectory. The planned closest approach was roughly 226 kilometers above Mars. The investigation's corrected estimate was about 57. At that altitude, the spacecraft was far below its safe corridor. As Mars filled the antenna geometry, the radio signal disappeared 49 seconds earlier than expected. The orbiter was likely destroyed in the atmosphere. The difference between the intended and estimated path was not created in one violent moment. It was accumulated, firing by firing, file by file, review by review. By the time the unit mismatch was obvious, the spacecraft was already gone. The famous lesson is usually told as metric versus imperial. That is memorable, but incomplete. Units were not enforced at the interface. Verification did not test the whole data path. Navigation concerns did not trigger a decisive escalation. The final correction was not operationally ready. Each layer assumed another layer would catch what it missed. Reliable systems make meaning explicit. They attach units to data, validate interfaces automatically, compare independent models, and turn unexplained deviations into action before the deadline. Mars Climate Orbiter was lost near another planet, but the failure happened much earlier, in the space between teams, tools, and assumptions. This is fault cascade, where small mismatches become system-wide consequences.